Hey everyone, and thanks for joining the AstrumDrive podcasts. Today, as usual, we're going to review our sprint. Currently, we're reviewing sprint 12, and we are going to see what progress did we do. And we're joined by Nelson this morning. Nelson, good morning.
Good morning, everyone. Good morning, Ivailo.
Nelson, thank you. Thank you for joining. So, Nelson, let's start from the beginning. Let's see what exactly did we do in the last sprint.
Sure. Well, the last sprint was really nice. We finally finished our first article and we submitted, and it was very exciting. And we are just waiting for the editors and some probably reviewers to give us the first feedback and start from there. So that's the very good news about this. That's this last sprint. But also made a lot of stuff. We check. Um, we're going into the next step, which is we are looking into special cases. Which are the special cases? Most people don't work out the equations. Oh, it's better to say they work out the equations. I mean Einstein's equations, but they don't solve the equations. Basically, you extract as much physics as you can from the field equations without solving the equations, because these are hard equations to solve, highly nonlinear couple equations. So it's complicated. It's not simple as just plugging into Mathematica, for instance, and get the solutions. Usually it crashes and it says there are no solutions for this. So it you need more complicated techniques, mathematical techniques. You need to prove the, that there exists a solution or not, and stuff like that. Anyway, we're going into this direction because we are also pointing into a future more oriented machine learning neural network way of looking for solutions, and this is like the first step. So what we start reviewing what are the best choices we can have as libraries, usually looking for Python written libraries that can help us to solve these special cases. And what are the special cases? Just a specific forms of matter with a specific equations of states, time and dependent and time independent situations. For the Einstein's equations we obtain from the spherical metric, we just submit the article. So this is what we're looking for. And we were looking for libraries. We found a couple. We started reviewing them to see if they have the capacities that we want. Some of them have some capacities but lack of others. We found some, for instance, that are oriented more in the in condensed matter and fluids. We have other that uses uh, only final elements to solve the equations. But anyway, each one of them have like their own uh, good thing and the lack of things, not bad things, but not useful for us at the moment anyway. So we're starting looking into that, and we're still doing. And if you guys have anything to say about this, if you have any suggestion, please go ahead and tell us. Uh, we review a lot. We also did some other stuff which are very exciting, and we were discussing right before the recording. We are looking into a problem which is a very fundamental problem, in the sense that it's a question. This is the type of questions that usually we can say naively any kid will raise these questions and ask what happens when an object is moving really, really fast. And usually this is straightforward. It has a straightforward answer, which is, well, you have a if you have a constant motion, you have inertial observers. You are in the context of special relativity. You have these moving objects, and you see that there is the distance between 2 points. That if you fix it in certain rest frame, then you see that this distance is contracted is there is a construction in another system, and you call this length contraction, which is not the same as Lorentz contraction, strictly speaking. I mean, they have like the same equations, but the interpretations are different. One, Lorentz came from trying to explain the Michelson-Morley experiment, and the length contraction is coming from the Einstein's special relativity. Anyway, the point here is like you have this, you also have time dilation, which is well known and well proven. It's been measured before. So, and what we're looking is to what happens to an object, but not now just the distance between two points, which is an theoretical way of looking at the problem. So the question is, what happens if you have an object, a real object, a rigid, massive object, and you just start moving really fast? And there are some articles that comes in this direction. And what we were looking for is that if we can somehow mimic or find something that is related to uh, like gravitational like effects. That's the best way I can put this question on the table. And it says, okay, if it's moving really fast and we have some length contraction, for instance, and what is going to happen with the object? Are we going to see different effects that comes from the observations we're making? And for instance, the light, the right the light rays that comes from the object are going to behave in such a way that it's going to resemble like an effect of gravity, even an effect of having some horizon and so on. Well, we know that this happens when you have accelerating objects. Then you have some sort of specific horizons. But what is it? This is question is this can happen if you had constant speed. If it's not, well, if it's not, then what happens if you are accelerating? And can we translate this into some sort of equivalent effect as in gravity? This is a question that arises because we are looking for uh, alternative ways of looking into fast traveling near the speed of light objects like a warp. I think it's the best way I can put it in this question. And we're looking into some of the literature, basic literature, that is approaching. I mean, this is approaching the question itself in terms of what happens to mass, what happens to rigid objects, and so on in special relativity. And it's amazing because I don't know if you guys knew, but there is no consensus about this. There are some authors that claims that this is just an illusion somehow, and some other authors say no, this is something very physical. And you have different point of views, and I'm talking about small authors. I mean, I'm talking about the great guys in physics. Some of them, like Born, they have specific articles saying yes, length contraction is there, and some others say no, there's no way. This is something that cannot happen, and they have their own reasons. And there is some still debate about this. But anyway, we're starting looking into this, and it's giving us in very nice directions and understanding, understanding a bit more this stuff like that are not well teach usually in the courses in the universities and so on. I mean, apparently they're superficially touch only, and this was my experience also. So this is very exciting to go into this direction, and these are foundations of physics, and we'll see if we can extract a lot of this for our drive research. I think we will. We also look into other very interesting thing, that is how to add electromagnetic fields into the energy momentum tensor. This is a good the next step is to add another type of matter and basically saying that okay, we are complicated matter. We already have anisotropy, we already have heat flux, we already have dust, and we already have perfect fluid. But what we want to include now charge matter, and this, which means electromagnetic fields. And this is not an easy question. It's not an easy task. We start looking into this, and the problem basically is how do you include a specific ways, a specific forms of electromagnetic fields. Uh, there is an easy way where you say, okay, you have an electromagnetic field and you put it, you just plug this in the energy momentum tensor. But what's the source of this electromagnetic field? That's the question. And the source have to be also there, which is part of the matter there need to be charged, and you need to have something there that is provoking. I mean, that is giving rise to these electromagnetic fields. So it's not easy thing to connect these two, to say I want this more or less simple electromagnetic field that I can work out, because it can be really get very messy. Well, what is going to be the source of this? Well, it's not straightforward that the source could give rise to this electromagnetic field and also give rise to the warp um, drive. So it's not an easy task, but we started looking into this, and we're going to start with uh, the most simple models we can find. But the good thing is we found a couple of articles that lead us in a nice direction, and we're getting there. We're getting there. That's the best thing I can say. We also make a lot of more studies regarding the lapse function. Basically, we recalculated some stuff because we we find out that we made a small mistake in defining one of the Illyrian observers, and when you include the lapse function, and we solved that, everything went fine. We have the same phenomenology, everything is okay, uh, and and we found that well, it works. It works very nice. One other thing that is uh, uh, we did is like we we look into the context of Friedman Robertson Walker cosmology to see an article the where this guy makes an interesting claim. This is, I mean, his result is like you the lapse function defines how you perceive time from different observers. Basically, it's telling you a way of connecting these observers, and and uh, and one thing that happens in cosmology, and this helps us to properly uh, interpret what's going on with the lapse function in our model. It's like if you have an accelerating universe that is accelerating, expanding long after the inflation. But you have this model that is describing now the universe. It means that you have some accelerating observer that is, let's say, riding this expansion, and this is the way that you should construct the metric from this observer. It's not a static universe, it's a expanding accelerated universe. So it means that you have an accelerated observer, and you have acceleration. It means that you somehow the, need the effects of to include the effects of time dilation, some time possibilities there. A bit difference because it's like having gravity in a sense. I mean, you have the Coulomb principle, and you have two different observers accelerating to each other. So the point is, like, if you put just the lapse function as it is in all the Freeman Robertson Walker universe models so far, and you put it to one, it means that you are forcing the system to say, well, if this one, it means that this is all this is going to happen. And this is, I mean, you're basically forcing to have some equation to state and so on. And this is not bad. I mean, describes very well a lot of things. But the point is, like, it's not perfect, which is in order to really make a good formal relation, you need to include a labs function that is different, and it's going to take into account that is going to be a difference between the servers. And some people claim that no, you can just gauge out this gauge function, labs function. But no, it's not possible. And these guys in this article, they prove it very very nicely. And the point is, like, if you have this labs function, then you get a lot of new possibilities because you're not constrained anymore to some questions state. You have you enrich more or less a bit your possibilities. And for instance, you can have models that might include negative energy. I mean, I'm talking about this dark matter, for instance. Somehow, these models, which I don't know really much about this, but I know this guy. You can include more complicated models, and this all applied also could apply in our metric because we have bubbles that so far are just static, but this could be the case that these are not going to be static the whole time. I mean, the bubbles are going to be formed and then going to disappear eventually to have a full trajectory of motion of traveling between 2 points. So this is a nice. It was a nice way to interpret what's going on with the labs function, and basically that's pretty much what we did during the last sprint.
Listen, that's really good. I just want to make several comments. So when you are talking about the special cases, it's very, very difficult mathematical problem. So we hired two mathematical experts to help us solving these partial differential equations. It's a really challenging problem. So, but based on the work we already put, I think that we have very good chances to find automated way of solving them. And the second comment I want to make is about the importance of adding electromagnetic fields. So I just want to remind some of our previous conversations in which we said that we want to find a way to automatically solve warp drive metrics. And not just one of them, we want to solve and evaluate hundreds of thousands of them. And we want to find the ones which can create like a warp movement but doesn't require negative energy. So our initial research showed that the electromagnetic fields are going to be very important for this research. Maybe we can form warp bubbles by using certain type of electromagnetic fields. Because of that, their addition is very, very important. So it's essential for us to add them, and because of that we put so much time and effort into adding these equations, which again is very, very challenging problem to add them appropriately and to make sure that we're doing the right thing. So those are the comments I want to make. So Nelson, do you have anything to say about that, or anything to say in general before we close?
No, not really. I think it's just you guys have any suggestion as you have done lately, and I'm very happy to read some of your comments. Please do. Please, we need all the help possible and all the ideas we can use, even if we lead us in very very complex directions. It is great. It is great. I mean, the challenging is not the bad thing. It's a good thing.
Yeah, that's actually, I'm very grateful because we got so many comments from our listeners and emails. So, guys, thank you very much for interacting with us, and thank you for sharing your ideas. Some of them are really good. Actually, we received several articles which were really useful for our research we didn't know before. So, guys, if you feel that you can say something useful, please share it with us. We're trying to read and respond to all the comments. And having said that, thank you very much for listening. And let me wish to all of you to have a very nice and successful week. If you like what we're currently doing, you can support us on Patreon, or you can share and like this video. With that, again, thank you, and I wish you a very nice and successful day.